Hello, here we are going to come up, or we need to come up with the characteristic equation of these two 3x3 matrices. And these equations that we are going to come up later are very important in solving for the correct eigenvalues, corresponding eigenvectors, and the representative eigenspaces of the two matrices. Now, to solve for the characteristic equation, we are going to use this given expression. You will have to come up with a matrix which is the result of multiplying lambda. In this case, that is a variable, but it has a specific value as we move further to eigenvalue because that's its symbol, minus a, the matrix that we are going to use for specific processes. Once we are done coming up with that expression, we will simply take out the determinant of the resulting matrix, and once we equate the determinant to 0, we will have our correct characteristic equation. But of course, one thing we need to look at is the presence of this I here. This is again the identity matrix, and this is not necessarily constant, as this depends on the type of matrix that we have. Here we have a 3x3 square matrix, so our identity is also the identity of the 3x3 square matrix. We have 1, 0, 0, 0, 1, 0, 0, 0, and then 1. So let's start with the first. Again, we have here lambda times your identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1 minus the first matrix A. You have 1, 2, negative 2, negative 2, 5, negative 2, negative 6, positive 6, and negative 3. Notice that we can see here our identity matrix and our given matrix are both 3x3. Hence, it is defined, or the difference of the two will be defined. But first, let's try to multiply the lambda. You have lambda 0, 0, 0, lambda 0, 0, 0, lambda. Minus again, you have 1, 2, negative 2, negative 2, 5, negative 2, negative 6, 6, and negative 3, which will give us this form here, lambda minus 1, so you have lambda minus 1. 0 minus 2 is negative 2. 0 minus negative 2, that's positive 2. 0 minus negative 2, another positive 2. Lambda minus 5, 0 minus negative 2 is positive 2. 0 minus negative 6 is positive 6. 0 minus 6 is negative 6. And you have lambda minus negative 3 is plus 3. Okay. Notice that in our final form, we don't have 0 entries. And hence, as we solve for the determinant, let us try to use the correct process of solving the determinant for a 3x3 matrix. Okay. So we will not be using the AD minus BC. Hence, we are going to use the movement from upper left to lower right as all positives, but upper right to lower left as all negative. So the first one is on the main diagonal, lambda minus 1, lambda minus 5, and lambda plus 3. Okay, so it might take a lot of spaces. Don't worry, I still have a lot of space at the bottom. You will have the next, negative 2 times 2 is negative 4, plus 6, that's minus 24. Next, or plus negative 24. You have 2 times 2 is 4, times negative 6 is another negative 24. Okay, so we'll have that for our first movement. The next movement, you will have it here minus all the entries from upper right to lower left. You have 2 times 6 is 12, so you have minus 12 of lambda minus 5 because you have this multiplier. Next, plus, but don't worry, we have minus here later. 2 times minus 6 is negative 12 times this, so you have negative 12, I'm gonna make it in parentheses, times lambda minus 1. Okay, and then plus the last one, lambda minus 3 times 2 times negative 2, so you have minus 4 of lambda minus 3. Don't worry about that, we just simply need to apply the correct operations. So let's not multiply this 3 binomial expressions here. Let's just stick with them. Probably we could see, sorry, that's plus 3, right? You have here. We might be able to see some items that we could factor out. So you have here minus 48, then minus, let's distribute the negative sign, 12 lambda minus 5. We'll have that. Then this is negative, and you have a negative here, so plus 12 lambda minus 1. And then you have here this negative, that's negative here, plus 4 lambda plus 3. You might see complicated forms here, but I would like you to bring you in this expressions here, okay? Because we cannot actually pick something that can be factored. Let's say, for example, we're going to pair this with x minus 1 here, but of course you will have this entire expression plus 12, so it will still have more complicated forms. Why do we choose this 2? Because when we multiply this, you will have minus 12x. If you're going to multiply this, that's plus 12x. In short, I mean not x, by the way, there are lambdas. So once you're going to do that, the lambdas here will be simplified, and you're gonna left with this form, to which you can actually factor with one of this later. So this is how it is done. Pardon with me. So you have minus 5. This is still lambda plus 3. This is still minus 48. Of course, this is minus 12 lambda. Okay. Then negative 12 times negative 5 is plus 60. Here, you have plus 12 lambda. As mentioned, that can be cancelled. Okay, let's just do it later. Then here, you have minus 12. Then, you just stick with this form here. Okay, let's just stick with that. Why? Because this is what will happen right now. Lambda minus 1, lambda minus 5, lambda plus 3. Notice, again, this will be cancelled out with that. This 48, negative 48 and minus 12 will have 60, right? So this is also to be removed. You just need to really examine the entries so that you could decide what to do. So we have here the last one, plus 4 of lambda plus 3. Now, we have a common here as mentioned earlier. So we can take it out. Lambda plus 3. So you will have this expression. Lambda minus 1, lambda minus 5, and you'll have plus 4 here. So this is lambda plus 3 times. Let's try to multiply this first using the FOIL method. You have lambda squared. You have minus 1 lambda minus 5 lambda, so minus 6 lambda. And then you will have this plus that. So you have positive 5 and then plus 4. Then lambda plus 3. Then you will have times here. Lambda squared minus 6 lambda plus 9, which is actually a perfect square trinomial. You can factor lambda plus 3 here. You can just simply say that's lambda minus 3 squared, or if you would like to, lambda plus 3 times lambda minus 3 times lambda minus 3. These are yet the characteristic polynomials. Once we equate them to 0, so you have lambda plus 3, lambda minus 3 squared, or the square of it, equal to 0, or lambda plus 3, lambda minus 3, lambda minus 3 equal to 0. These are both the characteristic equation of the first matrix. Take note, we are still on the first matrix. We have a lot of processes which involves decision making here. We are to decide here, but of course you just need to examine to that, because you will have very complicated forms here in this equation here. You just need to examine which can be simplified further. I just hope that my spaces here will be enough for the second one, because since our matrix, the next matrix A doesn't have any 0 entries, we might be able to also reach the same concerns earlier. But of course, let's just do it step by step. Lambda, identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, minus. You have 3, 2, minus 3, negative 3, minus 4, 9, minus 2, minus 5, minus 2 rather, and then 5. This is again lambda 0, 0, 0, lambda 0, 0, 0, lambda, minus 3, 2, negative 3, negative 3, negative 4, 9, negative 1, negative 2, and then your 5. Their difference can be expressed as this form. Lambda minus 3, so you have lambda minus 3. 0 minus 2 is negative 2. 0 minus negative 3 is positive 3. 0 minus negative 3, another positive 3. Lambda minus negative 4 is plus 4. And then 0 minus 9 is negative 9. 0 minus negative 1 is positive 1. 0 minus negative 2 is positive 2. And then lambda minus 5. So let's continue here. Will it be okay for you to allow me to do this so that you will have different process here? But of course, it may take a lot of space as well. Let's do it step by step. First, from upper left to lower right, lambda minus 3, lambda plus 4, lambda minus 5. Then, plus negative 2 times negative 9 is positive 18 times 1. So, plus 18. 3 times 3 times 2, that's another 18, plus 18. Okay? Minus all the entries from upper right to lower left. 3 times 1, so you have 3 of lambda plus 4. Plus, negative 9 times 2 is negative 18. So, negative 18 of this entry. Lambda minus 3. Next, lambda minus 5 will be multiplied with this. So, you have plus negative 6 of lambda minus 5. So, we will have this form here. Allow me to move a little bit lower so that we could really construct the next few steps. So, we'll have it here, right? Okay. So, the same. Lambda minus 3, lambda plus 4, then lambda plus 5. Plus 36, that's 18 plus 18. Minus 3 of lambda plus 4. This is negative times negative, so plus 18 of lambda minus 3. Then this is also negative, and then negative, so plus 6 of lambda minus 5. Now, which of the things here we could actually use to allow us to factor, sorry, is this minus? Yeah, I forgot to change it here, so let me go back here. This is minus. So lambda minus 5. Lambda minus 5. So which can be simplified, or which of this can be removed? Now notice here, when you multiply 18 and lambda, that's positive 18. This is positive 6. We have minus 3 here. Now, unlike earlier that you were able to examine that only 2 can be okay to be as simplified so that we could still retain this one here, why not try to multiply all of the entries here? So this is lambda minus 3, lambda plus 4, lambda, sorry, again, my bad. This is lambda, not x. Lambda minus 5 plus 36. When you multiply that, take note of distributive property. Minus 3 lambda minus 12. Okay? Here, you will have 18 times lambda, so you will have plus 18 lambda. Then you have minus 18 times 3 is 70. Sorry, not 72. The 54. Then, plus 6 lambda minus 30. Okay? Then, you will have lambda minus 3, lambda plus 4, lambda minus 5. Then, let's try to combine what can be combined here. Minus 3 plus 18. You will have plus 6. that's plus 21 lambda, right? Then you have 36 minus 12 is, or let's just simply try to use this one here, negative 30, and then you have this one here, negative 12 is negative 42, so that's minus 6 plus here, so you have minus 60, right? So you have minus 60. Now we can see here that if we are going to factor out 3 here, this will become 7 lambda minus 20, right? But nothing can still be factored together with this, hence it will not help us. This is one of the few examples where you can now manipulate the product of your 3 binomials here, so that you could see later if there's something that you could still further simplify. So once we multiply this first 2 binomials, then we multiply it to the third binomial. By FOIL method, you have lambda squared, you have minus 3 lambda here, minus 3 lambda, or let's just automatically add it. You have minus 3 lambda, but you have plus 4 lambda, so you have plus lambda. Then minus 12 times lambda minus 5, right? Plus 21 lambda minus 60. Let's check again. You have lambda squared minus 3 lambda plus 4 lambda. Okay, now let's try to distribute each of these terms to this binomial. So by distributing the lambda squared, you will have here lambda cubed, then to the other one minus 5 lambda squared. Lambda times lambda, you have plus lambda squared. Lambda times negative 5, so minus 5 lambda. You have minus 12 lambda plus 60. Then plus 21 lambda minus 60. As we combine all, we can now cancel this and further have lambda cubed. Sorry, let's make it better so that it will not look like x. Lambda cubed, this you have minus 4 lambda squared. This is minus 17 lambda plus 21, so you have plus 4 lambda. This is actually already an acceptable characteristic polynomial, and if you would like to equate this to 0, lambda cubed minus 4 lambda squared plus 4 lambda equals 0. This is already an acceptable characteristic equation because this is already final. But of course, as the purpose of characteristic equation and polynomial is to move further to eigenvalues, eigenvectors, eigenspaces, we can still represent this using like this one here. Okay, a product of 3 different binomials or expressions. The first one is we could factor out here lambda because all of the entries have lambda. And then what happens now is this is lambda squared minus 4 lambda, and you have here plus 4. Okay, now that we have that, we can now continue factoring this because this is a perfect square trinomial. You have lambda times that's the square of lambda minus 2, or you have lambda times lambda minus 2 times lambda minus 2. Okay, then if you're going to equate this to 0, so you will have lambda times lambda minus 2, or the square of it, equal to 0, or even you can use lambda times lambda minus 2 times lambda minus 2 equal to 0. These are correct characteristic equation, but of course, again, this is also the same as this. Now, before we end this video, as this is very long, take note that we see here multiplicity of binomial expressions. You have here 2 expressions of x minus 3. You also have 2 expressions here of x minus 2. This would mean that the equivalent, or the corresponding eigenvalue is also with multiplicity of 2. And we might have different eigenvectors for specific eigenvalues. But of course, we will have that for our next video. But for this, thank you for bearing with me. And this would be the process of solving the characteristic equation of our 3x3 matrix where there are no 0 entries on our matrices. Thank you very much for watching.